This new version of Newton's second law is more powerful in the sense that if you know how to interpret this, it enables you to predict certain things about the motion of a system of objects more easily. So let's look at that interpretation and three illustrative examples. This version of Newton's second law is telling us that a system of objects can be treated like a single object with these properties. A single object that has a mass equal to the total mass of the system, that is located at the center of mass of the system at that imaginary point, and that only accelerates in response to the net external force on the system, since any internal force pairs cancel out. And so if the acceleration of the center of mass of a system means the rate of change of the velocity of the center of mass of a system, then therefore this law is also telling us that a system cannot change the velocity of its own center of mass. Only something from outside the system, an external force, can change the center of mass velocity. So, illustration number one. Suppose we've got here an astronaut working on a space station, and we'll consider this the astronaut plus station system. Here's the center of mass of the astronaut in green. Here's the center of mass of the station in blue. And there, along the line connecting those two, in between them, in pink here, will be the center of mass of the astronaut plus station system. It's a little closer to the center of mass of the station, since the station's more massive than the astronaut is. Now, if the astronaut grabs onto this railing here to pull herself to the right, then the railing exerts a force on the astronaut, and the astronaut exerts an equal and opposite force on the station. So a moment later, the scenario could look like this. The astronaut has been accelerated to the right, but because of this force here, the whole station has accelerated to the left. The whole station has shifted left. But this N2L internal force pair represents the only forces on our system here. In particular, there are no external forces on this system. Therefore, there is no acceleration of the center of mass of the system. If this is zero, which means that the center of mass of the system keeps its velocity, which was zero. So the center of mass of the system stayed at rest. The point here is that even as the astronaut moved to the right and the station itself, the whole station shifted to the left, they did so in such a way that the center of mass of the system stayed exactly where it was. There's no way the astronaut can move around, pushing or pulling on the station, to shift the center of mass of the system. Only something from outside the system can shift that center of mass. It's a point locked in space unless something from outside comes along. Okay, illustration number two. Suppose our astronaut here, she has kicked loose from the station and is drifting off to the right. So here is the velocity of her center of mass. And although she can twist and turn and struggle and cause herself to spin around, there is no way for her to change her own velocity. If there's nothing from outside of her pushing or pulling on her, then the acceleration of her center of mass is zero. So her velocity of the center of mass is a constant. She is doomed to drift off to the right at this same speed forever unless something from outside pushes or pulls on her. There's no way for her to change her own VCM. Unless she finds that she has this enormous wrench on her belt. And if she picks up that wrench and hurls it as hard as she can to the right, then she is exerting a force on the wrench. The wrench will be exerting an equal and opposite force to the left back on her. So a moment later, here's the wrench now hurtling off to the right, and here she is still moving to the right perhaps, but more slowly. Nevertheless, since this is an internal force pair here for our astronaut wrench system, since that's an internal force pair and there's nothing from outside the system pushing on them, the velocity of the center of mass has to be exactly what it was a moment ago. So this small mass moving at a big velocity and this big mass moving at a smaller velocity can be combined to make a weighted average to find the velocity of the center of mass, which will be exactly what it was before. There is no way the astronaut and the wrench can change the VCM of that system. Although that might not matter to the astronaut, because she doesn't care about this wrench. All she wants to do is slow herself down and maybe even turn around. So if she has something else she can throw to the right, take off a boot and hurl it or something, she can continue to change her own velocity, but the velocity of the center of mass of the system of her and her tools, that cannot be changed unless something from outside acts. Okay, third example. This one actually has an external force acting on our system. So consider a ballistic missile here. It launches and then immediately after launch shuts off its engines and acts only under the influence of gravity. When we call something ballistic, we mean it's acting only under the influence of gravity. It doesn't have any engines of its own. So a ballistic missile is simply a projectile. And a missile or a rocket is often staged, as we say. It has multiple components that will break apart at some point during the flight. So at this moment, a explosive charge blows apart these two stages, and this second stage, this capsule here, gets launched up onto a higher trajectory, and the more massive first stage falls back down on this lower trajectory. So let's consider the two stages of our rocket a system. And in this case, there is an external force acting on our system at all times. It's the force of gravity, because the Earth down here is outside of our system. So the force of gravity is an external force. And in this moment of separation, as we're jettisoning the first stage here, the explosive charge will exert an equal and opposite pair of Newton's third law internal forces on the first and second stage. But that internal pair is not external, and therefore this explosion here, the separation of the two stages, has no effect on the motion of that imaginary point, the center of mass. The center of mass is not accelerated or affected in any way by this internal force pair. So beyond separation here, the center of mass of our system continues to move along the original trajectory. If we apply Newton's third law to the system over here, we'll see that the only external force acting on our system the whole time is gravity. Of course, the force of gravity on our system is represented by the mass of the whole system times little g, the gravitational field strength here. Mass of the system cancels out. And so the center of mass, that imaginary point, has an acceleration just equal to little g. It continues to move along the path that the rocket would have moved on even if it hadn't separated. So at these later times here and here, we can look for stage 1 and stage 2 and find them, and notice that the center of mass of the system continues along the original trajectory. Here at this later time, the center of mass of this system is still here along that original path, acting only under the influence of the external force, which is gravity.